Hello, this is David Harper of Bionic Turtle with an illustration of how to compute the value at risk of a bond portfolio for my FRM candidate customers. What I'm doing here is illustrating Philip Jorian's table 11.3 in the chapter on VaR mapping. So we're building on the tutorials I've shown in the last 2 days on VaR mapping. And importantly, our in-game goal here is to calculate this $2.63, which is, pay careful attention to this, an undiversified value at risk. It's not the diversified value at risk that we'll look at next. Therefore, it does not account for or give credit for diversification benefits in the portfolio. But it's useful nonetheless as an exercise. A lot of key concepts here in this table. So just to remind you, our portfolio has 2 bonds. It's a simple 2-asset portfolio. Both bonds have a face value of $100. The first bond has a maturity of 5 years with a 6% coupon. The second bond is a short-term bond, matures in only 1 year, paying a 4% coupon. So then we have one row for each year in the 5-year term to maturity. And in light green we have the future cash flows. Here, $110 in the first year. That's because this short-term bond is finished in the first year. There's the $100 principal plus the $4 coupon. That's $104. Now add the $6 coupon on the first bond, and we get a future cash flow of $110. Then at the second year, we only have the 6% or $6 coupon on the first bond, and so on until that first bond is finished with a return of the $100 principal and a $6 coupon. So these are the future cash flows of the portfolio consisting of the 2 bonds. Then we have, this is an input assumption, the theoretical term structure of spot rates. It's naturally upward sloping, and it corresponds to the yield on a 0 coupon bond. Then we have the discount factors, which are computed based on the spot rates. And so you'll recall a set of discount factors collectively is called the discount function. How do we get it? Well, if I just erase the year 3 discount factor, we know it's equal to 1 divided by 1 plus the spot rate in year 3 raised to n, or the number of years, the third power in this case. And this formula betrays that I'm using annual compounding. You'll note in the whole fixed income section we always say it's important to be mindful of the compound frequency. I could follow Bruce Tuckman and use semi-annual compounding, and that would be correct. In that case I would divide the spot by 2 here, and then I need to be consistent and raise to the 6th power, not the 3rd power. But I'll get a slightly different number, so we want to be mindful of the compound frequency. I'm following Jorian here. It's annual compounding. So I get the discount factors for each year. Collectively, this is a discount function. How do we use those? Well, we know these are just multipliers. If I'm here at the 3rd year, I say equals the future cash flow, that's the $6 coupon, multiplied by the discount factor. The point of the discount factor is to convert a future cash flow into a present cash flow. And what I get here is the series of future cash flows converted to present values. They sum to $200, the value of my 2-bond portfolio. And now we start the risk part, and Jorian here has risk percent. So maybe this is the hardest part in the table. I'm building now on the previous 2 tutorials from yesterday and the day before. This is really the returns value at risk based on this formula here, which before you add the VARs is just our basic duration formula. Here, the percentage change in the bonds, in the price of the bond, is approximately equal to duration multiplied by a 1% change in yield. And then we just add the VARs to it. So the returns VAR here on the left is a function of absolute value of modified duration multiplied by the yield VAR. This column here, risk percentile, corresponds to the left-hand side here, what we will call the returns value at risk. What does it mean? If we look at 3 years here, 1.48%, it means that given some level of confidence, our worst expected change in returns is negative 1.48%. We know it could be worse than that. This is for some given level of confidence. So we have one of these return VaRs for each year, each of the 5 years. And by the way, if this reminds you of the key rate shift technique, I think that's a good thing. There's a lot in common here with the key rate shift technique. It's essentially similar. And so now what we do with these worst expected changes in return, or the return VaRs, the risk at each maturity, we simply multiply that by the discount factor. So this 3-year discount factor reduces to 0.846. It's basically getting reduced by 1.48%, and then we recalculate the present value of the cash flow. Here you can see based on the new discount factor. So in other words, the $5.15, which was the present value of that coupon in the 3rd year, is now reduced by 1.48% to $5.08. See how the $5.15 present value is basically shocked or simulated down to 5.08, 1.48%. So all we've done here really is say if our returns value at risk, our worst expected change in the return is 1.48%, well, that means our 5.515 present value that we're expecting could be reduced down to $5.08. And so we're doing that for each of the cash flows. This first cash flow is getting shocked by 0.47%. That's the 1-year returns VaR. The second cash flow is getting shocked by just about 1%. And what we have here then is a sort of simulated series of cash flows on a present value basis that are based on the assumption that, or the simulation that, each of these returns VaR is realized. And so that gives us a new present value of the portfolio on $197.37, which represents our value at risk. Based on these returns VaRs anyway, our worst expected change in the portfolio is down to $197, or a value at risk of $2.63. But like I said, it's the undiversified value at risk, which will be the sum of the individual value at risks. So that's the explanation of the Jorian Table 11.3. This is David Harper, the Bionic Turtle. Thanks for your time.